start a new recording, and then we'll just go straight to my file from last night. Yes, here we are. Okay, transforming timber. I am proudly a part of that project, which my clicky thing is not wanting to play with me today. Let me just change port. Oh, there we are. So the question I asked you before is, why should we build using more timber in construction? Sustainability, you can grow it. And it's also it traps carbon. So that's what we're going to be talking about today. We've all heard of global warming. This is quite an old slide actually. I was quite embarrassed. I used this slide for the last X number of years, and I thought, okay, fair enough. But it is genuine. So I was checking this out last night for new information. It's the more slightly more updated. Stole this from the NASA website. It takes us up to last year. So you can see that trend growth, and you hopefully you'll see a lot of my references where I've borrowed material from. It's the effects of global warming. I know you know this stuff inside out, so I'm not going to baby you, okay? But let me show you some effects. This is my hometown where I grew up. It's actually Bathgate. Anyone from West Lothian? Okay, well, this actually isn't the effect of a heavy rainfall. That was actually an effect of something else, but the heavy rainfalls and things were contributing factors to it. There's a photo from my hometown. There's another photo from my hometown. This is due to heavy rainfalls. Bathgate again. This is France. Late last night, I came back from holiday and I thought, let's put some new slides in. You could easily find lots of photos of Perth. Perth had mass flooding a few years back. London, or outside London, the London Thames has massive flooding from time to time. You'll find lots of photos. So it's not just because it's time to time, it's becoming more and more frequent. As engineers, as structural engineers, we design buildings to be 1 in 50-year storm. 1 in 50-year storms are like 1 in 5 years now. I've got a story about a friend of mine who I'll not bore you. I'll not go off on a tangent, but there are situations now where it's evident there was 1 in 50-year storm. It's becoming more and more frequent. And the damage to buildings is quite evident. Anyway, this is also an old photograph, an old slide that I used. I thought it's well worth showing it, and it's the glaciers. The thing that's worrying about the glaciers is this statement here. More than 1/6 of the world's population rely upon glaciers and snowpacks for their water supply. That's quite worrying. Now, on the module that I was referred to before, which is the waste management, last year, I ran the module last year, I invited in a guest speaker. He came in, and I wish now he was the last or the second last lecturer of that cohort. I was kicking myself because I knew him as a friend. I should have asked him to open up the very first module, because he came in and he spoke. He's from I forget the part of India that he's from. He's from a part in India where he turned around at the very start of the lecture and said that he was a water migrant. His family, when he was a child, had to move village because of water. He was a water migrant, and I didn't know that about him. And after he said that, he had the audience in the palm of his hands, and it was really quite interesting. I don't have these stories. The only stories I've got are I grew up in that town. That's all I've got. Right, so we're trying to be realistic here. So 1/6 of the world's population are going to be affected. That means people will be moving. migrant people will be moving country to country or within countries just to access clean drinking water. I'll go through this quite quick and we'll go to the mathematical part. The causes. Greenhouse effect. Again, this is all babies. This is all stuff you got in primary school or stuff you've got early on anyway, yeah? Right. So, again, I'm not being funny. I actually stole this from a children's educational page. So I'm not kidding, right? This is babyish. However, it's really good. It's genuinely good. It's a good representation of the life cycle of our CO2, of our carbon, right? And again, I'm not going to go through that with you just now because I'm going to assume that you all understand the life cycle of carbon. If you don't, what we're about to go into in the next 5 minutes for the next half hour will become really difficult for you, so you better, if you don't understand it, put your hand up now. We're all good. Right. However, I do have notes at the bottom of that one slide there that explains that quite well. So if you do want to refresh your memory, there are some notes on the slide, so please have a look. What we're interested in then is the impact of the built environment in terms of CO2 emissions. There are two categories of CO2. CO2 is carbon dioxide, just for your just put your memory back in there. That's 1 carbon and 2 oxygen molecules. Who remembers the atomic mass unit? What's the unit of atomic mass? Who said that? Sorry. Yeah. Mole. I can't see lips move. Who said that? Yeah, right. Mole. You're absolutely correct.
John said it first.
Oh, right. Anyway.
Great street.
Yeah, okay, but I can't see people's lips move. Yeah, right, sorry. You're you're absolutely correct. So CO2 is 1 carbon, 2 oxygen, and it's in moles. There's another name for it as well. We've got the carbon dioxide due to the operational of the building. That's turning the lights on, putting the heating on, opening up the windows, all that nonsense. Yeah, that's the operational life of that. Now, think of it as, whilst we're here, think of it as, remember JC, Jeremy Clarkson, talked about years ago. He said that a standard petrol car, he said the operational life of that, the day that you buy that car brand new, has already accumulated carbon cost to build it. That is the embodied carbon. So out of the whole life of the whole vehicle, by the time it goes to the scrapyard, the day that it's brand new, it's already accrued the embodied carbon of 50% of its whole life, because of the cost of making a car is so expensive. Not necessarily financially, but carbon-wise it definitely is. And he turned around and said, which is very much unlike him, he said, the best thing for you to do, the most economic car, carbon-wise, in the world that you have, is the one that you could ever get, is the one that you've currently got. Keep it on the road for as long as possible. And only when you have to change it, then you change it. Not just change it every 3 years because you get bored of it. And it's very unlike him, but that's what he said. And it's interesting, when we look at buildings, it's a very similar story. When you look at a building, you build a building, which is the embodied carbon it takes to physically make it. It's a massive impact. Now, what we then want to do is make sure when we build a new building, make sure that its operational life isn't as costly either. So we'll have better insulation, so a better U value we call it, better air tightness. We can also have a thing called psi value, which is essentially it's a U value, but where the wall meets the floor and the wall meets wall, all the joints. Air tightness I mentioned. Then there's the heating and the cooling, the technology stack that goes inside that. So that's the two parts of it. So the operational is one plus the other gives the full life cycle of the building. It's a bit more complex than that. We're still at entry level here, okay? For us, for just now, That's a good enough assumption. That is that plus that. Right. Have a look then. So some estimates for the embodied CO2 for some common structural materials. I'm not anti-metal. I've designed an awful lot of buildings that use a lot of metal, right? And I've used a fair bit of concrete in my time, right? I'm not totally biased. Yes, I am. I am totally biased, but I'll be honest about it. Most of my buildings have been timber, but I've used a lot of metal as well, right? So my numbers are numbers that I've taken from elsewhere. They're not my numbers. So I'm just trying to be honest with you. Right, steel. We are talking about for embodied CO2, we've got 1,444 kilograms per tonne of CO2 equivalent. Right, it's CO2 equivalent. When we look at concrete, it's a lot less. Now, we'll have to bear in mind it says CO2 equivalent. Wait a minute, here's a problem. I'm meant to be biased. I'm meant to be... Hang on a minute. So for cube, 1 cubic metre, let's get our head around these numbers, right? For 1 cubic metre, which is what? That of steel, it's that much kilograms of CO2, tons of CO2 embodied in the environment, essentially, it's costing you. For concrete, yeah, that sounds about right. For timber, though, 390. That doesn't rhyme true, does it? You were saying it's environmental. But then you hit the nail on the head with it embodied. Right. Okay, well how do I get around this question? Because this is a hard question, isn't it? I can go out and I can go and make a cube of concrete for less than it would cost for the trees. Because I have to clear the land, I have to plant the trees, I have to manage the trees over a 30 or 40 year period, then I have to harvest them, and then I have to process that into construction timber. So these numbers there are construction timber equivalents, or pourable concrete equivalent, or rebar steel, or whatever steel that would be. Okay? So timber costs a lot, carbon wise. It does cost a lot. Where in context, concrete, I can go into the environment and I can plunder or steal from the environment raw materials that have been taken a millennia to produce. Or I need to plant that from scratch, or I can get steel ore or iron ore. Right. What about carbon sequestration, carbon lockup? That's what you were talking about. So, right. This is where it gets a bit more mathematical heavy now, and I'm going to use this as a whiteboard. Hopefully, is there a rubber? I don't think there's a rubber there, so I'll use this part here. Okay, now let's have a look at this then. The timber turnover timescale, or TTT, it's quite a log. That's horrible puns. Horrible puns, right. It's a log scale. Oh, that is terrible. Right. However, it is logarithmic, okay? It's a bad joke is what I mean. Logarithmic log. I cut down a tree and I make it into newspapers. Newspapers have got a shelf life of 1 day, or maybe a week if it's a magazine, or a month if it's a magazine. Right? So let's call it a year. The life cycle of that material, if it's turned into papers, let's just call it a year. Okay? Flat flat pack cycle is referring to your IKEA furniture. Buy a piece of IKEA furniture. To be fair, I've got lots of IKEA furniture that's lasted longer than 10 years. This is an average. 10 years they reckon an IKEA flat pack furniture might last. A building life cycle, we've got 100 years. So that's referring to like a house. As a structural engineer, you'll have to design buildings like a house for a 60-year guaranteed life cycle. As in the structure, you'll have to literally sign that off, your calculations and your indemnity insurance. However, you would expect an average building house to last 100 years. Expect that. Cathedral though, 1,000 years and much more. Anaerobic storage cycle. What does anaerobic storage cycle mean? With or without oxygen?
Without oxygen.
Without oxygen, thank you. So without oxygen, you get a big log and you chuck it on the ground and it's covered with other crap and there's oxygen's not getting to it, right? We've got a 10,000 year life cycle. Fossil fuel, now we're talking dinosaur juice there. Right. So the end of life options for wood. So my glue lamp beam or my piece of wood there. At the end of its life, it can either be repurposed, taken out of the building, put into a new one, cut to size and put in, or it can be recycled. Some way, shape or form, or it can go to energy recovery with CO2 leakage into the atmosphere, and you could also use offsetting, or it can go to landfill. We've got LFG as landfill gas, so we'll have to be taking note of that in a minute or two. Again, there's more information there. A little bit more about that. Right, so carbon 101, just meaning the basics of carbon. Very high schoolish, isn't it? Like high school, first or second year, probably second year, yeah?
Second year chemistry.
Yeah, so it's nothing hard, right? Nothing hard. But I'm going to write some numbers down, because if we don't, we'll forget. Carbon, C. That's annoying. That's genuinely annoying. Right, the atomic mass of carbon is 12. And oxygen 16. Good. GWP just stands for global warming potential. Over a defined time period with respect to whatever. Right. So the GWP of CO2, carbon dioxide, is as defined exactly as 1, i.e. it's the baseline. We use that as a baseline throughout science, okay? So that is the GWP is offsetted by CO2, and that's just a unit of 1. However, methane, write these numbers down. If I change slide, no, I'm silly, I've jumped ahead, do apologise. Right, so carbon dioxide is essentially CO2, so it's 12 plus 2 times 16, which is 44. So I write that up here, CO2 equals 44, and then methane, which is just C plus 4H4, so that would be CH4 is methane, and we're going to put that down as 16 as atomic mass, okay? So these numbers here are mass. I'll just put That's all mass, in fact. Okay, great. However, what we're seeing here is that methane, the stronger global warming effect, but has a shorter lifespan in the atmosphere. But we'll do it over 100 years first of all. So GWP 100, then we would have the effect of methane as 28. If we are saying that, another coloured pen, got another coloured pen on me. No, I don't. I do have that though, that's handy. Right, we're doing it all in green. Do apologise. Right, so the GWP of CO2 equals 1 GWP. Now that is all over 100, just so we know, of methane equals, that should be 28. On my slide here it says that is genuinely annoying. On my slide there at the bottom it says I'm going to refer to those numbers later on. If I were you, get a pen and paper, write down what I've written out on the board, just so you've got it. Yeah, be brutal. If it's the best you can do, it's good. Probably the window doing that anyway. I've done for something. In case we break it. Right. Got an example calculation, GWP for 100 years as a base for evaluation. What is the advantage of flaring? Flaring is burning off the gas. We see that all the time. Remember I said before I grew up in Bathgate? Across the Bathgate Hills to one side we've got Grangemouth. We see flaring all the time. A different type of flaring, but it's still flaring. So we use flaring in the real world. So as an example, GWP of 100 years, base evaluation, the advantages of flaring, i.e. burning 10 tonnes of methane from a landfill site instead of allowing it to vent into the atmosphere. We want to see what the advantage is. Is it better to burn it or allow it to escape into the atmosphere? That's what we want to check. As a baseline, it has a GWP of 28, so that means 10 tonnes of methane is actually 280 tonnes of CO2 equivalent released into the air if we allow it just to go into the air. If we convert that, assume all of the methane is converted to carbon dioxide. Now in reality, if you put a cover over a landfill site, you're not going to capture all of it. You'll capture most of it, but not all of it. You can get up to about 70%, I think. But anyway, we'll assume for this just now 100% is captured, and we've got 10 tonnes of it, and it's all converted into carbon dioxide if it's flared. So if we flare it, how are we doing that? Again, back to our high school chemistry. We're essentially doing CH4 plus, and what would it be? It would be 4 oxygens. Right? So 2 times oxygen, so that's actually essentially 4 oxygens. And that's just the oxygen in the air, so all that is. We convert that, so I'll just write it here as well. I'm going to take a photo of this afterwards, plus 2 times oxygen. Essentially it's that. By the time you burn that, that's going to end up creating let's just do it manually. That out, C with the O2, and then I'm going to be left with, now H4 is the equivalent of 2H2. Would you agree? Because that is just 4, 8. It's just a 4, right? and that's the same. So they equals the same. I just do of course I just do that there. That's what's left. What have I got now? What's that? Did that. Excellent. Don't be shy. Water. So when you flare, you're creating CO2 and water. That's what you're creating. Right. So you're literally creating water drop. It'll probably be in droplet form, cloud form. It wouldn't necessarily be puddles of water falling off, but it could be, depending upon the temperature where it goes about. So that's what happens there. The mass of CO2 emitted from by doing this would be 10 tons. Right. The 44 is this. So we've got, hands will be covered in blue ink. 10 tons times 44, what is originally 16. That makes sense to you. If that doesn't make sense to you, please sit and look at this slide, get a pen and paper out. All we're doing here is we're saying we've got 10 tons of methane. Methane is the 16. The mass of the methane is 16. Sorry. Thank you very much. Sorry, sir. Right. The mass is 16. We're just playing with mass at the moment. Yeah, we want to know the mass. Right. So we'll go 16, but we've converted it to CO2, which is 44. So it's 44 divided by 16, and it's 10 tons of it. So that equation there gives us 27.5 tons. So, we started off though, if we were to allow the gas to escape into the environment, it would be 280 tons of CO2 equivalent. That's what we said. However, if we flare it, what's it actually costing us is 27.5 tons of CO2 equivalent. So the improvement is 280, take away 27.5, the improvement is 252.5 tons of CO2 equivalent. Or i.e. it's 90% better to actually flare that than it would be to just allow it to go into the environment. You could then turn around and say, well, actually, what happens if I used that to heat a house instead? If I heat houses, that would then be totally carbon neutral. Right, so that's fine, that's landfill. Why are we talking about landfill? We're meant to be talking about wood, aren't we? Let's talk about wood. You know how, what was the moisture, can anyone remember the moisture content of the first lab? What was the sample moisture content? 10%. That's really quite good, isn't it? Because 20% would be normal in a house. That's what they reckon's the average. So when we dry down our wood for testing, laboratory testing, we get it to about 12% is what we try and do. And we do that by having it at a temperature of 25 degrees and humidity 65% is what we do commercially, when we do this commercially. And we're trying to get it to an equilibrium at that temperature, and for softwood that would be about 12%. That material there has been sitting in the lab for years, but it's had no moisture in the air at all, probably. So 10% is pretty decent, and you'll probably find that's about 10%. I've got a device here. I'm not going to put it into my lovely piece of wood because that's too nice. and I've brought it for another reason. But this is a moisture meter, and you can measure the moisture of things. Put 2 prongs in. Another way of doing it. It's not as accurate as what you did. Your way is much more accurate. Right. Getting back to my point then. So the average wood is usually about 12% moisture content if it's indoor service class 1. So if I've got a piece of wood that's 224 grams of wood, say, find water will be 12% of that, so that'll be 24 grams. So let's negate that first of all. Let's just imagine we put it in the oven for 24 hours and it's totally bone dry now. So it's 200 grams of wood now. You'll find 50% of that, i.e. 100 grams, will be carbon, and the other 50% will be three gases, H, N and 0. And we'll talk more about that in a minute. And that is the weight, the mass. The carbon though, so the gases will go, they'll just go into the environment. They will go into the environment. However, the carbon is a bit we're interested in. You got 100 grams of carbon. Some of that will go into storage. About 90% of it will go into storage, i.e. it'll fossilise. Not fossilise, it's the wrong word, that's a different thing. But it will decay to a level and it will stop. However, 10% of that will become LFGs, which is, what does LFG stand for again? Landfill gases, yep. So that's 10%. 50% of that, which is 5% of this, become methane. And the other 5% become CO2 emitted. And from that methane, some can get captured, but not all of it. Some of it will be emitted, because you're not going to capture all of it. It's not really that possible to capture 100%. We're going to try and capture as much as we can of that methane. So, landfill carbon maths. Already covered that top part there. So oven dry part, almost precisely 50% of the carbon, i.e. 100 grams. Wood is a mixture of cellulose, hemicellulose, and lignin. Lignin's the glue. I've given you my packets of straws and talked about straws before. The lignin, lignin doesn't degrade without oxygen. Right, anyway, it's a reasonable assumption that after a long time, timber frame, only 10% of the wood will have decayed. So only 10% of the wood will have decayed by a long time. Landfill gases is assumed to be a 50-50 mixture of methane and carbon dioxide, so 5 grams each. Approximately 70% of the LFGs is captured, the rest leaking into the atmosphere. So the emissions are therefore 5 grams of carbon in the LFGs. CO2 equates to, well, it's 5 grams times 44 for the mass, divided by 12. 12 come from again? Carbon. Yep. Which gives us that. Carbon, yep, which gives us that there. Fine. 1.5 grams, which is emitted into the atmosphere, i.e. we couldn't capture it. So that's the 70%, that's the 30%. Emitted as CH4, which is methane. So that equates to 1.5 times 16 mass divided by 12, because remember it's carbon. And we're multiplying that by 28. which is the GWP effect. This is the effect of the methane. 3.5 grams that is captured amounts to a zero impact if utilised, or 9.6 grams if flared. You work out the maths on that quite easy. So the total emissions, essentially that plus that gives you 74, or it's that plus the effect of that gives you 84. Right. So this is the part that I'm going to say. This is a worked example here, and in your class test you're going to have one similar to this. Right. I haven't written it yet, so I don't know exactly how it's going to go, but one would imagine it'll be very similar to this. Let's just pay attention if we can. Right. Read through it first of all, and I'll then explain what will probably happen in your class test, and I'll confirm it to you once I've written it. I need to submit it for approval, so like Wojtek will approve it for me. You'll have to sign it off once I've written it. So for this example here, what about incineration? 100 grams of wood. So just for clarity here, I burn wood in my house. I have a wood burning stove, so it's relevant for me. It's maybe not relevant for you, but it is relevant for me and for a lot of people. Right, 100 grams of wood carbon will emit, but this is not the wood oxygen and hydrogen and nitrogen, it's the wood carbon. So it's that 200 grams, it's that 100 grams of carbon we're talking about here. Will emit 100 times 44, which is the CO2 plus, divided by 12, which is the carbon, because it's from the carbon, which is 364 grams of CO2 directly into the atmosphere when burnt. Okay, so that's not very good. That's actually quite bad. So for a tiny bit of wood, 100 grams, I'm actually putting into the environment CO2, greenhouse gases, of more than 3 times of the weight of the wood itself. So it's not a good thing. However, if the energy is recovered from, say, heating instead of, if I'm using that to heat my house rather than using fossil fuels, what's the effect? So the calorific value of what? Let's have a look. Perfect, right, this is good. Right, so the calorific value, so CV of wood is approximately 5 kilowatt hours per kilogram of wood. Right. So this isn't quite a kilogram, but just imagine that it's a kilogram of wood. And kilowatt hours for roughly that there is kilowatt hours for that there. That's what I'm going to get if I burn that one piece of wood there. A kilogram. So with 100 grams of wood, carbon is 224 grams wood. Will produce a 1.1 kilowatt hour of heat. So for a tiny bit of wood, which is 100 grams, which is probably, I don't know, the size of that of softwood maybe, will produce 1.1 kilograms of heat. However, methane, in this example here, we're using methane. In the example that you'll see in your class test, it will be natural gas. It will be piped gas from the grid. right? But for here, we're assuming I'm comparing burning a piece of softwood, or hardwood even, but roughly this size. I'm comparing it to methane, captured methane from a landfill site. That's what I'm comparing. So the calorific value is approximately 15 kilowatt hours per kilogram. Now wood is only 5, but for methane it's 15. Remember, a kilogram of methane is a substantial volume. It's per mass, it is significantly better than wood. The quantity of methane needed to produce 1.1 kilowatt hours is 1.1 divided by 15. So that's how much gas I need, or methane gas that I need, 73 grams. Remember, I only had 224 grams of wood at 12%. Right? So it's mass-wise a lot less. This would produce 73 grams multiplied by 44 divided by 16 of CO2 when burnt. So taking the offset into account, the emissions of me burning my wood and offsetting it against having methane and not burning methane instead, would actually be only 168 grams of CO2 equivalent. Make sense? In your exam, or your class test, you'll be asked to do a very similar thing to that. It's just that I'll be giving you data based on not methane, but natural gas. Question?
Will you give us the
Yeah.
mass of the gas or just the chemical form?
No, you won't have the internet. You'll not be doing this in the house, you'll be doing this in the class, closed book, which means I'll give you all the data you need. It's a second year module, right? And I'm not trying to trip you up. And it's not going to be the bulk of your coursework, your exam. This will only be a small little part. Try to capture those. Try to get a first class.
How many marks would a question like this be worth?
Don't know yet. That's what I was just saying. And it's not going to be the bulk of your exam. The bulk of your exam will be the questions that I've already given you some extra ones of. I've given you extra material for your first week 2, week 3, and week 4 I've still to give you extra material on. That's where the bulk of your... If you want to just pass this module and no more, just do that other stuff. If you want to get a first in this module, you get on top of the class type of thing, you'll need to do this as well. So don't spend as long on it as you would do other stuff, is what I'm saying. I will give you a breakdown of what's in the class test beforehand, and if you want, I can even give you a mock. We'll have a look at that if we've got time for a mock test or not. It might be good fun. I like that. I say it might be good fun, yeah. No, it won't. Right. So we'll see. It'll be something like that there. I thought I'd leave this slide in. This is meant for my 5th years. In the UK alone, 5 megatons of 5 MTs of wood waste per annum. 50% of that is from construction and demolition. The rest is from other sources. Approximately a third of this is recycled, so not all of it. Particle board, fibre board are the main pathways to high. If I told you this before, the OSB, that's an image of OSB by the way. OSB is one of our biggest exports in Scotland. Salmon, whisky, oil and OSB are probably the next one after that, after the other ones. It's a massive export for us, and so we use an awful lot of recycled material in the making of OSB. So yeah, I'll leave that slide in there anyway. Right. As a matter of fact, now we're getting to the latter end. What time is it anyway? We'll make some decisions.
11:45.
probably do a similar thing to last time. Do you want to do, we've got a tutorial to do for Excel. You want to do a similar thing to the last time, is try and do that and not prolong the whole day. Yeah, let's do that then. Right. As a matter of fact, using timber in construction material helps by tackling global warming. Now, my caveat to this is bullshit. Sorry, I never said that. Strike that from the recording. That's not factually correct. In my opinion, and not just my opinion, people within my field that I work within, we upfront say that using timber as a carbon sequestration is not the answer to global warming. The answer to global warming is stop burning fossil fuels, for one. All that we're going to do by using more carbon sequestration, i.e. planting more trees, is going to slow down the effects. Is all we're going to do. If that's the only thing that we do as a country or as a world, is just plant more trees, yeah, we're in for a real hard time really fast. So, caveat to that is, it's only going to slow down the process, but if that's the one thing that we can do as engineers throughout our life, is to try and encourage our clients to build out of timber where it's appropriate, only when it's appropriate, not when it's not. The reason why I say that is, you don't want to build a building out of timber where it wasn't appropriate, then in 10, 20 years time or 30 years time, you rip it down, put a new building up. That's not appropriate. You want to build a building with trees or wood that last longer than it took to grow the tree in the first place. If it took 100 years to grow that piece of wood there, I want that piece of wood to remain out of the atmosphere, i.e. not to be burnt and not to rot away longer than the time it takes to grow the tree. Preferably, I want that to be kept in the cycle of construction for as long as possible, or never allow it to rot. That's what I want to do. Okay? Right, so we'll go back to what we should be talking about then. Right. Timber structures are lighter than steel. Right, okay. On my hobby horse now. So timber as a construction material, its strength to weight ratio is better than concrete or steel. Bamboo, anyone you ever used bamboo in construction before? Napier would do a lot of bamboo research. Johnston does a lot of research with bamboo. Bamboo has got a tensile strength stronger than steel, but it's got other properties that are not as good. But if you then combine bamboo with other materials, it can become really quite interesting. You can make very large beams very, very small just by putting bamboo and with timber in the right places. I discussed that before with you guys in first year about the second moment of area. I definitely did discuss that. Timber construction's faster, typically 15 to 20% faster construction than other materials. But that's more to do with MMC, modular methods of construction, which we're not really talking about in this module. That's for Kenny Leach for third year. You'll get him. This is a project one of my students done it. We paid for the work. It was a Bext intern, and we designed a small building. We actually built 15 of them in real life in a forest in Fife. Say we didn't build them. Other people built them, we just designed them. And they're like holiday homes. However, by building that little holiday home, it sequestered carbon enough to take out of the environment 2,768 kilograms of CO2 equivalent. That is just a number. When you convert that to, for example, reduction of essentially my car for a year, actually a bit more than what my car would do for a year. I'm roughly on average about 10,000 a year. So just by building one little building like that, that includes the other things as well. It's the equivalent of me not driving a car for the year. However, that's simple. It's a simple little building, a little bothy and the... Remember your project from last year with me? Similar to that. However, if we look at a standard house, it's a semi-detached house. It's a 3-bedroom semi-detached. Now in England, we build masonry systems, brick and block. Okay? If we use that as a benchmark system there, and we build the exact same house, but not out of brick and block, but timber frame and block with render on it, it's equivalent of roughly 4 years of a family car off the road. If we say, no, wait a minute, I'll do a closed panel rather than an open panel, again, if you're in my class last year, you'll understand the difference between the two. But for those that weren't, it just means you're using more OSB, another sheet of OSB. It makes the building significantly stronger, and it also means I get to have bigger windows and bigger garage doors and things like that. I'm not allowed to have them in the first place. That would mean an equivalent of taking an average car off the road for 8 years. If I go even more mental and take away that external brickwork and I put on a render board onto the house instead, but roughly taking a car off the year for 9 years. If we're building 200,000 new houses a year, if we can convince, now in Scotland, 92% of all new house starts, low-rise house starts, are timber frame anyway, but probably that one. If we were to convince them to say, well, actually, if we were to do this style, or better still, that style, that's in Scotland. In England, it's only about 25% of all new house starts currently, it's relatively new data, 25% of all new house starts in England are timber in any way, shape or form. Actually, essentially that's a benchmark. So the more we can convince people to use timber only when it's appropriate, then we can make a massive difference if you multiply that by new house starts a year. Right. That's the end of this lecture. I'll stop the recording. Or do we want to talk about the coursework for today? We probably should. Probably should. So you already know how to do the mathematics. You already know how to do the... Where's the mouse? Let's see. Oh, sorry. Which one? So just for the recording, I'll show you again where the extra material is for the coursework, for the additional material for week 2 and week 3 is here. I've not given you the answers. You'll have to work out the answers, show me your working in class, and if I like it, I'll give you what I've got. If you don't do it, I'll hang off until you do it. I'll give you the answers out, because that would be just pointless, because you need to do the work. If you do the work, I'll promise you you'll pass. If you don't do the work, it's more difficult. So please give it a bash, then I will give you the solutions. Then next week, I'll give you additional material for week 4. Now, for coursework number 2, which I've not put online yet, but I will do later on today, but I'll show you the brief. The brief is pretty much the same as before. However, okay, this is not the sample that we have. You'll see it go down in the lab later on today. The load's going this way this time. Okay, and you've already taken part in my lecture. The lecture's now put online from last week, 2 weeks ago, sorry. It's now online. I loaded on it last night, I apologise. So, you won't have any excuses there. The brief's exactly the same. Your marking is exactly the same. Your framework or your what's not framework. Your framework for your document should be if you get 100%, say you get 100% for your coursework that you submitted last night, and your framework's good, so that means your presentation and readability will be good. Then all you'll have to then do is just work on your technical content, figures, and then some conclusions to get those marks.
Because I'm assuming it's not the 11th of November.
This is, as I said, I'm going to modify this. That will then end up saying, please look at Moodle, is what it will say. Just so I can keep it for next year. Right. So that will say, please look at Moodle, is what it will say. Apart from that, there'll be no change to this document other than, please look at Moodle.
I mean, when will that one?
Yes, I'll give you that 2 seconds.
Alright, cool.
And there's some notes there again. And there's the math. There's a simple gist of how to do the maths, but you should know that anyway. And there's that framework which you've already got now anyway, from the exact same as before. Right. So, question was, when is this due? Teaching schedule. Coursework 2 is given out today. Is due. It's given out today there, right? That's fine. It's due back in on the 10th. Okay, it's pretty soon. Next week. It's easy though. It's really easy. If you come to the tutorial just now, if you do this tutorial just now, 1 o'clock now, isn't it? If we go to a tutorial for half an hour, 45 minutes max, if we do that, I think then it'll be easy. It'll be really easy. As long as you can understand how to do the thing that's different. And what was different? Fmax. Fmax was different, wasn't it? Right. As long as you can do that one thing, find that Fmax properly, then as long as you get a good mark in the first one, then it'll be copy paste. If you don't get a good mark in the first one, check back the recording of that other person that did get a good mark and see what was different. Yep. And change yours, and you'll be fine. So, how about what we do?
Question, because on the brief it said like 700 words, but I wrote quite a bit more than that. I don't
care. I don't care. I don't like these word targets. I think it's absolutely horrendous. Because my framework was about 700 words, was it not? My brief itself was massive. So if you took, where is it? If you just copy and pasted that in its own self, I don't know what, 200 words or something just for that? Yeah, 700 words is never going to happen. Yeah, 227 words just for that. Absolutely pointless. I'm going to remove these targets from next. Where does it say 700 words? Just so I know. Does it say it about?
Down a bit. That table.
Yeah. I'm going to remove that. Because it's not helpful. You now see what somebody else done for 100%. Don't go bonkers. You're not writing a dissertation. So, do we want to go to a computer suite and just jump onto computers? Is that what we want to do now? I will just do that now then. I'll stop this recording. If you follow me, so we all go together rather than going off. And let's just try and do it really as fast as we can. I've only got one thing to show you on it. That's all I've got.